Vincent. I'm a system and network engineer, and I work at Bedrock as lead of the cloud architects team. 3 years ago, I talked about at the first HAProxyConf about Kubernetes and the ingress controller, HAProxy ingress controller we are using. But today, I will talk about load balancing algorithm and streaming. Bedrock Streaming is a tech company. We build a streaming platform that we sell as a white label basis to our customers, media companies in Europe. So basically, they take care of the contents, and we take care of their platforms. It's a B2B2C model. 50 million active users are using our customers' streaming platforms. And each platform is quite unique, as our customers can choose between different business models: advertised VOD, subscribed VOD, or hybrid of both, which is most likely what the top players like Netflix or Disney are leading to. Sometimes at Bedrock, we can help a customer launch a whole new platform, a whole new service, like we did with Salto 2 years ago. But we can also help a customer migrate all its users from an active platform to the Bedrock managed one, like we did with Videoland this summer. In both cases, that would lead to the video cache layers to be empty, waiting for users to actually ask video streaming. So the VOD origin of the CDNs must be ready to handle the load. We also want to remove the technical barriers to be able to publish a lot of contents all at once, which means if a customer wants to publish all the Simpsons episodes at once, that could be a challenge for the VOD origin. So we want to remove those technical barriers. Also, we are using multiple CDNs for each customer to improve the end user experience, also to reduce costs, and sometimes to respect some partnerships that our customers may be having with local ISPs. So the origin of the CDNs must be ready to handle the load. And more importantly, we need 3 things. The VOD origin must be performant, resilient, and cost-effective. But what is a VOD origin anyway? A video is a static file. It's easy to store. And just put a CDN as a cache layer in front of the storage, and there is no much problem. Well, when it comes to streaming, there is an extra step, video streaming, which is called packaging. Packaging aims to give some control to the player, so the player can switch between different audio tracks and video qualities during the watch. So when you watch a video in streaming, you actually start by downloading a manifest file. It's the same on Netflix, on YouTube, on Videoland. You start by downloading a manifest file, and the manifest will describe a lot of metadata of the video: duration, video qualities, audio tracks, and everything. And then the player can start downloading the video. But the player won't download the whole video file at once. It will download 6-second duration video chunks. With only 6-second video chunks, the player can adapt to the user's bandwidth by switching from one quality to another. And cutting the one video file that is stored on disk on several 6-second duration chunks, this is what is packaging. We do packaging just in time, so when the user actually asks for a specific chunk. So on the storage, we store a whole video file. We have a CDN in front that accepts requests from our different players. And then in between, there is a USB origin that will do this just-in-time computation. With this just-in-time, we have the benefits of doing things dynamically, but still we can cache the answers on the CDN, so we have the best of the 2 worlds. On-premise, we had this platform that worked really well for more than 10 years. We had an Nginx cache layer to absorb the load. Beside, we had the USB origin servers doing this just-in-time packaging. and we were using a scality ring to do the storage of the videos. At the time, Bedrock had only one customer. It was not a problem, but then we have now 5 customers, and we expect to have many more in the near future. So we wanted to have auto-scaling on this platform, and also customer isolation, so that customer A cannot access video of customer B. We achieved that at Nginx level with some vhost rules, but we wanted something better to really split the traffic between different customers. COVID-19, during lockdowns, people consumed a lot of video streaming, and we started to have problems and stability issues on this on-premise platform. So we said, okay, in July 2020, we migrate this to AWS. We came up with this first version, the cloud-based version of this VOD Origin. We wanted to use most possible network managed services at AWS, which means the network load balancer to have a single TLS endpoint. Because we have different CDNs, we want to have a single TLS endpoint to configure everywhere, so we can be CDN agnostic. We wanted to have auto-scaling on the compute using the CPU or bandwidth usage to scale up or down our servers. And we would be using S3 to store the video. This is actually a skeleton, as all our customers have dedicated AWS accounts, so this platform can be deployed on all customers and can scale dependently. So we can achieve both scaling and isolation. Before going to prod, we did some load tests. It's nice to do some load tests before going to prod. And it went really well until we had a problem. We reached the limit of 5,500 get per second on a single S3 bucket, which is not really a problem, because we know that S3 is able to scale over time. But we didn't expect to reach this limit so early, because we were doing a load test of only 2,000 get per second. So we said, OK, why do we reach this limit, and how can we push it further? Under the hood, when a player asks for a chunk to USP, USP receives a request, but is unable to process the request directly. It needs to do 3 more calls to the S3 bucket. The first call will be the manifest. 2 other calls will be the video metadata that are stored in the first 65 kilobytes and the last 15 bytes of a video. And then USP will be able to compute the exact chunk length and give it to the user. We said, OK, those metadata, they are the same for all chunks of the same video, so we can cache them. We said we can cache them locally on the USP servers. We would benefit from that because at the time, USP wasn't very familiar with TCP keep alive, so it was good for us to also put a proxy between USP and the S3 bucket. And also, we know a lot Nginx because we use it on our private CDN, so it's not the perfect tool, but we know its weaknesses, so we are very OK to work with Nginx. Also, one of the good features of Nginx between USP and the S3 bucket is when you use it as a cache proxy. If we send several different requests to Nginx, but they concern the same object on S3, Nginx will actually do only one request to the S3 bucket, and the other request will be in queue. And when Nginx will receive the response from S3, it will respond to all connections that USP sent. So we can lower the number of connections to the S3 bucket thanks to Nginx and the cache. Metadata caching can be really effective, as we don't need a lot of gigabytes locally on the servers to cache a lot of metadata for hours of video. So it can be really cool to cache locally on the server. If we want to cache locally on the USP Origin servers, there's a problem with the load balancing algorithm, as the network load balancer at AWS only knows two load balancing algorithms, round robin and least outstanding request. Both those load balancing algorithms are not fit for cache servers. In this example, we have one load balancer and two cache servers. That would lead that any cache server can respond to any request with round robin or least outstanding request, which means if we take all the video traffic for the red heart connections, it can go the first on the first cache server, then on the cache 2, then on cache 1, then on cache 2, which means every cache server is a duplication of the cache. And it's even worse when we scale up. Each server is still a duplicate of the cache, and we don't specify the cache. The cache is not specific to a part of the cache. So if we scale up with round robin or least outstanding requests, we will pay more for fewer performances, for worst performances, which is not what we expect from scaling. This is why consistent hashing is very much more suited for caching, which means for the same red heart connections, they will always go to the same caching server. So the cache is not duplicated on each server, but it comes specific to a server. And it's even better when we scale up, because every cache server is even more specific, so we benefit from the scaling, and it's even better. We wanted to add another AutoScaling group running HAProxy. So HAProxy will do this consistent hashing on the different cache servers, and we can add some local cache on the US per region servers. As Willy told in the keynote, sometimes adding a layer in your architecture can actually benefit in terms of performance or cost efficiency or a lot of other benefits. That means two levels of load balancing. The network load balancer will be doing round robin, and HAProxy will be doing consistent hashing. We wanted to keep the network load balancer as we want to have a single TLS endpoint to configure on all our different CDNs. Using HAProxy, we have two problematics. The first is using consistent hashing, we need the backend configuration list to be exactly the same on all HAProxy instances for the consistent hashing to stay consistent on different instances. Also, the network load balancer is able to do some discovery thanks to the target group. But HAProxy needs something to do the discovery, to populate its backend servers. We ended up to use HAProxy to build HAProxy Service Discovery Orchestrator, which is a simple Python tool that aims to do exactly that. So it's a client-server model, which means the server will use the AutoScalingGroup API to update the ready servers list in the AutoScalingGroup. This list will be sorted and stored inside a DynamoDB table. The client runs alongside HAProxy and polls the DynamoDB table regularly every X seconds. And every time there is a change, we use the Runtime API to update HAProxy servers. So there is no file management, it's only API calls. Inside DynamoDB, we can store a lot of information. Either the servers are enabled, disabled, the IP addresses, instance IDs, the weight, and a lot of information. Everything that can be necessary for the client to create the configuration inside HAProxy. On the client side, we can connect to the Unix socket thanks to this little Python code. So we connect to the socket, and as you can see on the last line, we can send a command to the socket. Those commands can be really simple, as we can change an IP address or a port of a server. We can also enable or disable a server. We can change the weight of a server. In any case, we never create or delete servers. We only modify them. We keep track of the running configuration of HAProxy with the showstat command, and we compare the showstat command, the running configuration, with the desired configuration that is stored inside DynamoDB. So the client always tries to reach the desired configuration. Because HAProxy HSDO controls all the backend configuration, the backend definition in the HAProxy config file is quite simple. We use a server template with the same size as the AutoScalingGroup maximum size. And as you can see, the servers, they are disabled by default, which means when HAProxy will start, when we scale up HAProxy servers, the configuration will be empty. There will be no backend server available, so HAProxy won't be usable until HSDO configures HAProxy. We tested again with production workload, and we achieved what we wanted, which means a good cache-hit ratio and Nginx, which means better performances and fewer calls to the S3 bucket. Still, we can observe in the cache-hit ratio some sudden cache drops. That happens when we scale up the cache servers. So when the cache server, a new cache server enters the game, it will start with 0 cache. So it needs some time to create its local cache. We wanted scaling to be really part of the design of the platform, so to lower the impact of scaling cache servers and to have the less impact of the end user experience possible. So we configure gradual ramping up of servers with HSDO, which means when a new cache server enters in the AutoScalingGroup, it will start with a very low weight in HAProxy, and HSDO every X second will increase the weight of the backend server, so the backend server can have time to populate its cache. This is what you can see between the red line, which is the connections that HAProxy sends to the backend server, and in blue the cache-hit ratio, which slowly reaches its perfect behavior. We wanted to go further on the optimizations before going on production. And one of the unwanted behavior of consistent hashing is that sometimes few servers can be really loaded, while the majority of servers are doing nothing. In our case, it's a problem because we use the AutoScalingGroup scaling policies, which are averages, which means if all the servers in the AutoScalingGroup are not using CPU or bandwidth all at once, we don't scale. So we wanted to harmonize the load between all servers inside the same AutoScalingGroup. We're using consistent hashing with bounded loads to do that. The bounded loads will allow to overflow the request of a single server or to another server, which means when there are too many connections to one server, the connections can be overflowed to another server. This allows to harmonize the load between all servers. But more importantly, the consistent hashing with bounded loads, they respect consistent hashing, which means when we overflow, we always overflow to the same server. So we keep a good usage of the cache, even when we overflow. As you can see on this graph, we tested with and without the bounded loads, and with real production usage, you can see on the first graph that 2 servers were loaded, while the majority of servers were doing nothing, so we couldn't scale up. But with the bounded loads, we achieved exactly what we wanted, which means an harmonization of the load between all servers. In HAProxy, the hash balance factor is a keyword that, which allows you to configure the bounded loads value, which means in our case 140. One server can have 40% more connections than the average of servers in the same backend. We had the idea to use the bounded loads because we were at the first HAProxyConf, and we assisted of the talk by Andrew Rodland from Vimeo. They implemented the bounded loads in HAProxy a lot of years ago, and we benefit from their work, and that gave us the idea to do the same in our platform. Before going to prod, we also wanted to improve resiliency. And there are a lot of limits on AWS around the networks. The bandwidth can be rate limited. But also, we have a limit around the number of packets per second on a single server. As you can see, sometimes, and almost every time, some packets are dropped by AWS, even when we don't reach the full capacity of a server, but sometimes packets get dropped. And in both cases, and also when we have microburst is when we reach the quota in less than 1 second. We can experience queuing or maybe drop of packets. We can impact performances, and which can lead in bad user experience, end user experience. We found out that when HAProxy needs more than 20 milliseconds to open a TCP connection to the backend server is more likely in bad shape. So we prefer to not use this backend and to fail over another server. So we're using a timeout connect of 20 milliseconds. Also, both S3 or USB Origin can answer badly with bad HTTP codes. So we're using the retry on keyword to retry in those situations. In the end, the configuration is quite simple. On the default section, we can find the timeout connect of 20 milliseconds. We have several retries. We use a retry on keyword, and we're using the redispatch option, which allows us to fail over another server when the first is unhealthy. The redispatch, they happen all the time at a very low rate, but they happen all the time. We consider it's part of the design of the platform. And that means that we regularly have problems either on the packets per second or around the bandwidth on our servers. But because it's really part of the design of the platform, we haven't modified much in our configurations. We were confident to go on production. So in September 2020, after working on the second version, we started to migrate our on-premise traffic, VOD traffic, to this V2. And there were a problem. The V2 is too expensive. We discovered the EC2 other cost. OK, somebody knows about the EC2 other cost. The EC2 other is part of the EC2 world, but it means the entire availability zone traffic. Actually, by design, the network load balancer can send any request to any HAProxy instance, whatever the availability zone. And also, HAProxy can send requests to any cache server, whatever the availability zone. It turns out that the entire AZ traffic is a financial abyss for us, and it's billed the full price by AWS. And it could drown the project. So we wanted to change the design to limit this inter-AZ traffic. We thought about duplicating every servers, each on their dedicated availability zone, and to configure HAProxy so that it would only use servers in the same availability zone. It was actually quite simple to do that, as we duplicated the AutoScaling groups. We dedicated the AutoScaling groups to a single availability zone. And we configure HSDO client to stick only for the servers in the same availability zone. So it was actually few hours of work. It also turned out that with this V3, we are more resilient to an AZ failure, as is one of the AZ is failing. all the traffic can be sent to the only surviving availability zone, which will have all the cache. With this v3, the cache is duplicated in each availability zone, which means we still can send requests, can answer requests to the end user with good performances. We deployed this v3 in November, and as you can see, all the bars are increasing between October and December because we were still migrating our on-premise traffic from on-premise to the cloud. And as you can see, the orange EC2 other cost dropped to almost 0. We took the shot of this v3 to also create a fallback backend. So basically, with the v3, HAProxy will only take care of the cache servers in the same availability zone. But if there is a problem, we want to be able to use any usable servers, whatever the availability zone. We are willing to pay more if there is a problem, because we want to be able to give an answer to the video at any cost. We switch from the main to the fallback backend with this simple ACL. If there are not enough servers in the main availability zone, we just use the fallback backend. Finally, the cost of the EC2 instances are not so high, around 15%, because we are using EC2 instances, spot instances. On AWS, spot instances are servers for which you pay 68% less, but at any time, AWS can send you a reclaim notification. And once you get the reclaim notification, you have only 2 minutes to finish your workloads before the server is shut down. In our case, it's not a problem, because everything runs at few milliseconds. HAProxy servers are stateless and are configured through HSDO, so it's not a problem. And the application servers, the cache servers, they can both scale up and be reclaimed. HSDO, with a gradual ramp-up, will not have an impact on the overall usage. As you can see, the network load balancer, which is only doing some round-robin, consumes a lot more money, costs a lot more money than all the EC2 instances combined. You need to follow some policies, some rules, if you want to use a network load balancer or a load balancer on EC2 spot instances. You should use at least 12 instance types, different instance types, and also mix instance families. Like, don't use only CPU optimized or memory optimized or network optimized families, but mix them all to avoid mass reclaims. You should also prefer small servers and a lot of small servers than few big ones to avoid the impact when you get reclaimed. And finally, but this is not specific to spot instances, you should really take care to the baseline versus the up to capacity, bandwidth capacity of EC2 servers. The up to bandwidth that you can find in the main documentation at AWS, they refer, we can see on this C7G.medium that the bandwidth capacity is up to 12.5 gigabits per second. And if we look closely, you can see that this is a burst-able capacity that is not guaranteed, not even for 1 second. And you should refer to the baseline capacity instead to know what you are actually able to use. And deeper in the documentation, you will find the baseline capacity. For the same C7G.medium, you can find that it's actually 24 times less than the up to capacity. So we fell in the trap. Maybe you shouldn't fail in the same trap. Is it time for the next version, for the v4? So basically, the v4 will imply to get rid of the network load balancer. As I mentioned earlier, the network load balancer is a huge cost in the platform. But it's not really Yeah, we can get rid of the network load balancer, but that would imply that we would expose HAProxy servers publicly, and we need to find a solution so we can still be able to scale our HAProxy servers to hundreds of servers without impact and without to do any configuration on the CDN side. We want our CDN's configuration to be agnostic, so we need to work on this next version. But there's no rush for this, because the V3 has a really good uptime, and actually it's way better than what we had on-premise. So there's no rush for the V3, for the V4. Finally, what I wanted to say today is that we achieved to do what we wanted, which means performant, scaling, resiliency, and cost-effective platform, VOD Origin. We are using both AWS and HAProxy APIs to achieve that. And it's been made easy for anyone to run your load balancer almost everywhere. At least you have an API. So maybe you can do the same. Thank you, everyone, for listening.
Thank you, Vincent. Wonderful job. Thank you.
Thank you.
So again, if you're in the audience, please just raise your hand nice and high, and one of our mic runners will come out to you. And we're also taking questions in the stream. We already have one here. Or we're waiting to get the mic over here. I can ask one from the online audience. So Vincent talked about customer isolation and video storage. Did you face any challenges with customer isolation and traffic management, like security, routing, QoS? And if so, how did you solve those challenges?
No, we haven't on this specific VOD Origin platform, as we're using CDNs, and they all implement WAF, so we don't really need to do some security on the origin side. But still, we are using an HAProxy configuration that ensure that the request comes from a CDN and not directly through the network load balancer. So we can drop any request that is not authorized from a CDN. This is kind of a security, but not.
We have one back here. Yeah. Irish.
Hey, sorry if I missed this, but the HSDO looked really interesting. Is that available to other people? Did you guys open source that? Yeah, we open sourced it. Actually, if you watch the replay of this presentation, there is a link of the open source, the GitHub repo that was done the HSDO explanation. So, thank you. Sorry, I was a few minutes late, so I missed no problem. That. And actually, I think HSDO, it's kind of a duplication of the Fusion project that the HAProxy team is building. So maybe it's worth to go to the Fusion documentation instead, because it may be the next future of the project, of the HAProxy project.
Thank you.
Sorry. Hi, Vincent.
Hi.
Regarding HSDO,
yeah.
Just to understand, so it's a kind of central component that will talk to the various HAProxy? Okay. Because I thought that maybe that could be also kind of nice contribution to the data plane API itself, instead of having, trying to use the data plane API in mix with that.
We thought about using the data plane API, but we couldn't control the list of the servers inside the same backend. And using AWS and consistent hashing, we need to ensure that the server list is exactly the same on all HAProxy instances. And we just thought it was easier to run the Runtime API.
Yeah, that's what I meant. It's a feature request or it's a contribution. That's
okay. Okay.
There's another one from the online audience. So you've had several iterations of your platform. A lot of people may be hesitant or scared to tear down and rebuild a working solution, let alone do it multiple times. So what drives your team to keep improving?
Sorry, can you repeat?
Yes. So you've had several iterations of your platform, and you've had to tear down and rebuild multiple times. Yeah. And that can be scary. What drives you to keep improving and going through that process?
I like to keep the idea to do some release and some short release with a known release plan. So we know which feature will be in which release. So, okay, we said we want the V1 to be quickly usable, but without much feature. We want for it to be quickly usable, even it's never saw any production workflow. So we're using also Terraform to use the infrastructure as code to really ease the deployment of all the different versions. And actually, it's quite easy to just add some features. We said it's the V2 or the V3 or other version, but it's only how we mention them. Actually, it's a single platform. We just added an AutoScalingGroup or modified an HAProxy configuration, but it's not a whole new platform of really different behavior. It's the same platform.
We have time for one more question, right here.
Regarding your ramp-up of a new server that you had, did you try the slow start directive on the server line? And if yes, why did you need to do something different? I'm interested, in fact.
Yeah, thank you very much. I wanted to mention it, and I forgot. But we don't use the slow start configuration option of HAProxy because we want all HAProxy to have the exact same behavior at a time. And because we scale both the cache servers and HAProxy servers. That means if there is a new cache servers that enters the game, it will benefit from the slow start configuration in HAProxy. But if 2 seconds after a new HAProxy servers is added, it won't use the slow start. So the behavior won't be the same on all HAProxy instances. That's why we wanted to centralize the weight configuration of this platform. Thank you.
Thank you so much, Vincent.
Thank you.